irrational numbers. This is our last topic, topic 7, irrational numbers. We have finished with rational. When you study rational, you already got an idea of what is irrational, okay? So irrational numbers are real numbers that cannot be expressed as the ratio of two integers, okay? More formally, they cannot be expressed in the form P over Q, where P and Q are integers and Q is not equals to 0. You know that this expression here, this definition here is for rational numbers, okay? This is for rational numbers, okay? So if a number can be represented as P over Q, where P and Q are integers, and Q is not equals to 0, then it's a rational number. If it cannot be expressed in this manner, then it is an irrational number. That means any number that is not rational is irrational. So we have our real number set. Okay, our set of real numbers consists of two sets here. Okay, one is rational numbers Q and the other one is irrational numbers. Okay, so real numbers consist of rational and irrational. If it's not rational, it's irrational. Okay, so one characteristic of irrational numbers is that their decimal expansion does not repeat or terminate. Okay, example pi 3.14159265359. If you look at this number carefully, the digits after the decimal, they do not repeat and they do not terminate. They go on and on. Okay, therefore this is a rational number. E equals to 2.7182818 and so on. It doesn't terminate, it doesn't repeat. If you look at the digits carefully, it doesn't repeat. This is also a special case of rational numbers. Pi and E are special cases of rational numbers. Square root 2, you know, it's 1.4 something, and it goes on forever. So this is a rational number. Square root 5 is a rational number. Okay, these are some examples of rational numbers. Okay, so next we are going to look at some properties of rational numbers. Okay, properties of rational numbers. Okay, the first property of rational numbers, the square root of any whole number. Square root of any whole number that is not a perfect square is irrational. Okay, that means we have examples here and say non-examples. Okay. The square root of any whole number that is not a perfect square is irrational. That means square root 5 is irrational. These are examples of irrational numbers. Square root 9 is rational because this is a perfect square. Square root 9 is 3, therefore it's rational. Square root 7 is irrational. Square root 25 is rational. Square root 7 over 2 is irrational. Square root 9 over 4 is rational. Okay, same thing with cube numbers, cubic numbers. Cube root of 64 is rational. Okay, cube root of 8 is rational. Cube root of 8 is rational. Cube root of 7 is irrational, and so on. Okay, cube root of 16 is irrational. Okay, so these are examples of rational and irrational numbers. Okay, this is the first property. Second property. Second property is regarding addition. Okay, the addition of an irrational number and a rational number gives us an irrational number. Okay, that means when you add an irrational number with the rational number, you get an irrational number. Okay, so for example, if x is an irrational number and y is a rational number, the addition of both the numbers x plus y is an irrational number. Okay, let's look at some examples. Okay, example 1. if you have 3 plus square root 5, 3 is rational, root 5 is irrational. So 3 plus root 5 will give you 3 plus root 5 is 2.236067977 and so on. Okay, so this gives us 5.236067977 and so on. So when we add a rational number with an irrational number, we get an irrational number. This just proves the property. Okay, example 2, 4 and 1 3/4 plus pi. Okay, 4 and 1 3/4 is a rational number, pi is an irrational number. So when you add this, 4 and 1 3/4 is 4.333. It is repeating. So that although it's not terminating, it's repeating, so it's a rational number. Plus pi is 3.141592. This is non-terminating and non-repeating. Okay, so you get we get a number like this, and it goes on forever, non-repeating. Therefore, this is an irrational number. Okay, so these two examples prove to us that when you add an irrational number with a rational number, you always get an irrational number. Okay. Okay. So the next property of this is the third property of irrational numbers. Multiplication of any irrational number with a non-zero rational number results in an irrational number. Okay, if we don't look at the word non-zero, it is just the same like addition. Multiplication of any irrational number with a rational number results in an irrational number. Okay, so let us assume that x, y, z is rational. Then x is equals to that y is rational. Okay, let's do an example here. Okay, so this is multiplication. I have one rational number here, 3 multiplied by pi is 3 pi. Okay, so this is irrational. Okay, example two square root 2 number. Okay, so multiplying a rational number with an irrational number gives us an irrational number. Okay, why do we say non-zero rational number? Because if you take any number 0, say 0, and you multiply it with say pi, pi is irrational and 0 is rational because it's a whole number. So when you multiply this, you get 0, which is rational. Okay, so anytime you multiply by 0, you get rational. So only in this case, this property does not apply. Therefore, we have this word here, non-zero rational number. Okay, so far okay? Okay.
Okay, madam.
Okay, so we have one more property here. The addition or the multiplication is the property number 4. Okay, the addition or the multiplication of two irrational numbers may be rational. Just now we said that rational and irrational will give you irrational. Now, the addition and multiplication of two, when both the numbers are irrational, it may be rational. Okay, the product or the addition may be rational. For example, root 2 multiplied by root 2, you get a 2. Irrational times irrational gives us a rational number. Okay, that is one example. Okay. Another example, 4 root 5 plus 3 square root 2 gives us the same number, okay, because we cannot add this. So this is irrational, okay, this is an irrational number. Or if we have 2 plus root 7, okay, plus negative root 7. They are both irrational numbers, okay. When you add these, you get 2, which is a rational number. So when you add or multiply two irrational numbers, you may get a rational number. Okay, this is the fourth property of rational numbers. So I think we have run through rational numbers. So I think you sort of know what are rational numbers are. Okay, let me give you an example for multiplication here. Okay, for multiplication we have says root 5 times root 5. Both of these are irrational numbers. You get a 5. This is a rational number, or root 8 times root 2. Okay. These are both irrational numbers, but when you multiply, you get square root 16, which is 4. And this is rational. Okay. So sometimes when you multiply or add two irrational numbers, you can either get rational or irrational. Okay. So we have looked at the properties of irrational numbers. Okay. Golden ratios. Okay. Golden ratio is an example of irrational number. Okay. The golden ratio of pi. Okay. This symbol here is known as pi. Pi represents golden ratio. It's a special number approximately equal to 1.618 and so on. It continues. Okay. It doesn't repeat and it doesn't terminate. Therefore, it is a irrational number. Okay, the number 5, often known as the golden ratio, is a mathematical concept that people have known about since the time of ancient Greeks. It is an irrational number like pi and e, meaning that its terms go on forever after the decimal point without repeating. Okay, so how can we define or show this golden ratio? Okay, demonstrate this golden ratio. Pi can be defined by taking a stick and breaking it into two portions. Okay, so if you have a stick like this and you break it into two portions, okay, so this, say the length of the original stick is A and you have this length B and C, one shorter than the other, B shorter than C. Okay, so if the ratio between these two portions are the same as the ratio between the overall stick and the larger segment. That means if the ratio between C over B is the same as A over C, if this is the same, then it is said to be in golden ratio. Then this is in golden ratio. Okay. Okay. Okay, let's look at this diagram below here. Okay, this is this. You have seen this picture before, right? This follows the Fibonacci square, which is also in golden ratios. Okay, so if we look at the length of or the dimensions of this rectangle here, it's a rectangle. Okay, we know that the length of A is, what is the length of A? Okay, what is the length of this rectangle? Length, width is A, length is A plus B. So we know that the length is A plus B and the width is A. Okay, let's find out what is this ratio. So how much is our A and B here? If you have 34 here, you remember this Fibonacci square? If this 34, it means that the dimension is 34. Okay, so this length here is 34. What is this length here? 8. What is this length here? 13.
21.
When you put together, what do you get?
21.
34 plus
21.
over A is
34.
34, correct? Okay, when you divide that, what do you get? Do you get 1.617647059 and so on? This
Yes.
is approximately 1.618, right? And this is the value of the golden ratio. Therefore, this rectangle has a golden ratio. Okay, therefore this rectangle is also known as the golden rectangle. Okay, there are many objects or many designs around us that follow this golden rectangle. For example, your bank cards or your credit cards, okay, they follow this golden ratio. They follow the golden ratio. If you measure the sides, the length and the width, and you take the ratio, you will find that it is almost 1.618. Okay, this golden ratio is like people like it. It's like very pleasing. So they like to use golden ratios. Okay. So let's see how we can draw a rectangle or a golden rectangle. Okay, we're going to see how we can construct a golden rectangle. This is our application part, okay? Okay, to construct a golden rectangle, we start with a square. Construct a square A, B, C, D. Okay, so we have square A, B, C, D. So this is a square, which means all the sides are the same length. The side can be any length. You can construct a square which has a side length of 3 centimeters or 5 units or whatever you like. Okay, so say this is A, B, C, D. This is same length. So let's just say that I'm taking this side to be 3 or maybe 5. Let's use 5. Okay. This is 5 and this is 5. So all the sides are 5, okay? So in step 2, I'm going to construct the midpoint E of DC, okay? So this is my A, B, C, and D. I'm going to construct the midpoint, okay? So find the midpoint here and label it E. You can use a compass to find the midpoint, okay? Using construction principles, we can find the midpoint E, okay? And then from E, you're going to draw a line from E to B, okay? Okay, I'm going to draw a straight line, okay? Okay, so from E, draw a straight line to B. Can you tell me, can you calculate what is the length of B? What is the length of EB, I mean? Okay, I told you that this side here is 5 and 5. And you know that E is the midpoint. Therefore, what is this length here? DE or EC. What is this length here?
2.5.
Yes, 2.5, or we will use fractions, 5/2, right?
Yes.
5/2. So if this EC is 5/2 and BC is 5, how can I find EB? How can I find the length of EB? Using what?
Pythagoras.
Formula. Yes, correct. Using Pythagoras formula, okay? So I'm going to find the length of EB, okay? So EB will be 5 squared plus 5/2 squared, 5/2 squared, whole thing square root, correct? So this is square root of 25 plus 25/4. So what do I get? If I solve this, what do I get?
5.59.
Or in fractions, it will be, this will be 100 plus 25/4 square root, right? So this will be 125/4 square root, which is equals to, is this 5/5? Square root of 125. Okay, it's 5/5/2, okay? So this is your answer. So we know that the length of EB is 5 root 5 over 2. Okay, so we know length of EB is root 5 over 2. Now, okay, now we are going to draw a circle. But before we draw the circle, actually we can draw this later or we can draw it earlier. Okay, so 1 minute. Okay, so I'm going to extend this line DC. Okay, this line DC, I'm going to extend it, make it longer. Okay, and this line AB up here also extend it, make it longer. Okay. Okay, so now we know that the length of EB is 5 root 5 over 2. So what I'm going to do now is I'm going to draw a circle. I'm going to draw a circle or an arc, okay, using EB as the radius, okay. So I'm going to put my compass here, E and B, okay. Then I'm going to measure EB and I'm going to draw a circle so that it intersects this line here at F. So when you draw a circle, it will be like this. It will cut here like that. Okay, a circle. So maybe we can draw a nicer circle later. Okay, so it will cut here, intersect here at F. So what is the length of EF now? What is the length of EF now?
5.
I used EB as a circle. I used EB as the radius and I drew the circle, the arc. So what is the length of EF? This length.
5 square root 5 over 2.
Yes, 5 root 5 over 2 because EB and EF, they are both the radius of the circle. So they are the same length. Okay. So now one last step is draw a perpendicular line from F to line AB and label it as G. This intersection point is G. So now you have a rectangle that is AGDF. Okay. So now let's see if our rectangle follows the golden ratio. So how do we know if our rectangle follows the golden ratio? We need to find the ratio of, say, DF over AD. What is DF now? What is the length of DF? It is DE plus EF. DE is 5 over 2 plus EF is 5 root 5 over 2 over AD is 5. So what do we get here? 5 plus 5 root 5 over 10, right? Okay, you tell me what's this in decimals.
8.36.
Again, check again. You do the top first and then divide by 10.
Okay. So 1.618.
Yes, 1.618 and so on. Okay, so this we know is the golden ratio. So we have learned how to construct a golden rectangle with golden ratios. So you can start with any square here. Okay, you can even use a square with the sides of 1. It can be 1 unit. 1 can be 1 cm, can be 1 inch, can be 1 unit. So you take a square with the sides of 1, the bottom side divide into 2, get the midpoint, join the midpoint to the opposite corner or the opposite vertex and find this length. So if this is half, this is 1, using Pythagoras theorem, we will find this length is square root 5 over 2. Now using this as your radius, draw an arc and let it cut here at this intersection here. Therefore, your radius and this length is also 5 over square root 5 over 2 because it is the radius of the circle. Then you can find the whole length of the rectangle is 1 over 2 plus square root 5 over 2. In this case, 1 over 2 plus square root 5 over 2 divided by 1, and this is 1.618. So this follows the golden ratio. Okay, so this is how you draw a golden rectangle that follows the golden ratio. Okay, class?